Alright folks, Unit 2, 31% of the exam, motion in one direction. Spent a lot of time on this in the year and I think it's pretty important. That's why it's 38% of your exam, 38 multiple choice questions. So we got vector, magnitude plus direction, scalar is just magnitude, and then we have the three types of velocity: constant, average, instantaneous. Examples of each of these, and this is gonna be tough because there's not a lot of room here, so I'm just gonna kind of like abbreviate the best I can. You know, cruise control plus you have to be going on a straight path, you know, same direction. Because remember, this is velocity, which is a vector, so it matters. Average, we have the total distance over total time, meaning that, you know, sometimes you might be going faster, sometimes slower, but it all kind of works out and you get an average. For example, if we drove 50 miles in 2 hours, our average velocity would be 25 miles an hour. Instantaneous, this is when you look down at your speedometer, but it's just for a fraction of a second. So it's instantaneous. At that one instant, what is it? Average velocity is pretty simple. It's not as hard as the magic physics formulas. It's just taking the distance over the time. This will show up later down here in our VDT chart that we will be working on here in a little bit. Let's knock out the vector scalars, as this is always a fun game to play. So we'll say mass, that's a scalar, velocity is a vector, acceleration is a vector, speed is a scalar. Remember, speed has the vector velocity. Distance, that's scalar, but displacement is vector. This is distance plus direction. You know, this has two as well. Density, scalar. You can't put direction with density. Momentum, vector. Impulse, vector. Force, vector. So all these are vectors. Remember, these are almost the same thing, momentum and impulse. We really haven't studied that yet. We didn't quite make it to that far this year, but you're still held responsible to it. Just knowing if it's a vector or scalar in the units. Acceleration is the rate of change of velocity. Rate of change of, and then we got velocity. That's why it's meters per second, or meters per second squared. 3 accelerators in your car. This is tricky as well. Most people would say, oh, you just have one, it's your gas. But remember, we can also slow down. That's also considered acceleration. There is no word deceleration. That's a dirty word in physics. We don't use the word decelerates. Steering wheel, changing direction. Remember, it's acceleration, which is a vector. Therefore, if we change our direction, we've changed it. If you go in a circle with your cruise control on, technically you're accelerating. Average acceleration is the change in the velocity over the time. Once again, this is easier than the magic physics formulas, which we're going to get to in a little bit. But to be honest, you know, you can do pretty well on this exam with only knowing number 3 and number 1. Unless you choose to do throw it up and miss it, then you should know them all. But of course you can graph that. But we digress. Alright, so free fall, 3 conditions. Acceleration, which is gravity, is 9.8 meters per second squared. Starts at rest, so V naught equals 0 meters per second. And then finally, there's no air friction, no air. Another way to say that would be vacuum, V-A-C-U-U-M. Need to have these 3 things to be truly free fall. Now we have some free fall equations. So these get the job done when you start at rest. V equals gt. This is coming from magic physics formula number 1. We've just neglected the initial velocity. And then we have d equals 1/2 gt squared, which is the same thing. It's coming from magic physics formula number 3, but it's starting at rest, so we get rid of v naught and d naught. Now we're ready to do some free fall problems using these 2 equations. That's what I mean. Like, if you know the free fall equations, you don't really need to know number 4. And you don't really need to know any of the other parts until you get down here to T catch. Person drops a rock in a vacuum from a height of 100 meters. How far does it fall in a second? So we use d equals 1/2 gt squared, and we would put in 100 for d, and then we can put in gravity, so we'd get 4.9, and then you just have to solve for t squared. So we divide by 4.9 and square root, and so you get an answer of how long does it take to fall 100 meters. Whoa, I jumped the gun here. Sorry about that. That would be down here, and this would be 4.5. I didn't even look at the questions. What am I doing? How far does it fall in a second? Okay, it always falls the same. It's 4.9 meters. How fast is it going after the second? 9.8 meters per second. And then finally we get down to the one I tried to answer at the beginning, which is how long. What's the velocity when hitting the ground? So we can use this right here, which is our shortcut from Magic Physics Formula number 1, but we can just use V equals GT, put in 9.8 here. We can take our time from our previous answer, 4.52. So if you made a mistake on the time, sorry, you're going to mess up the velocity. And we get 44.3 meters per second. What if you dropped a feather? How would this change your answer? Well, it turns out that it wouldn't change the answer at all. So there would be no change. And the reason there's no change is because in a vacuum, everything falls the same. Whether it's a rock or feather, it doesn't matter. They still accelerate at 9.8 meters per second squared. Okay, we get over here to our VDT chart. Velocity, distance, time. Remember, this is impossible to actually do, but we keep it like this because it makes it easy to do the math. So you can't immediately go from 120 kilometers per hour to 0, but that's what we're going to assume to make the math easy. So we're going to say 120. This goes here. And they also tell us for 30 minutes. So notice that I preset the units for you, and I said half. So we'll say 0.5. And now we go back up here to our average velocity equation. Where was that at? All the way up here. V equals dt, or V d times t would equal V. So if we want to know what d is, we say V divided by t, and that will tell us. And so we end up, multiplying by a half. And when we do that, we end up with 60 for our distance. Once we have that done, we can go on to the next series. So it says for 30 minutes, you wait 2 hours. So we have 2 down here, and nothing happens, just staying put. And then we have a speed, returning speed, south versus north, making it negative, returning at 50. 50 in an hour. So the hour goes there. And that's how we got negative 50. I put in the wrong spot, but it didn't matter because this is easy to do. So we end up adding these up and we get 3.5. And then our distance we end up with would be 10, so we don't ever make it back all the way. We get close, but we don't quite make it back. In terms of our velocity, remember I said we're holding a constant for half an hour, so that we'll say that's half an hour right there. And then for 2 hours, we're not doing anything. Then we're going the other direction. Not quite as fast, but we're doing it longer, twice as long. So we come over here like this. You can shade these in because remember this is the integral part. Like we can take these areas and we can plot the areas here, and we'll get these different things. So now we go up, and then we come over, and we go back down. And we never quite made it. We made it to 10, but we didn't make it all the way. And so that's where we end up, is right here in our position time graph. This slope may be a little too steep. Yeah, that looks a little bit better. Remember, it's a lesser speed, so therefore we don't have quite as steep a slope. Alright, one more to do, and that's t-catch. T-catch can be very confusing. Let's write out magic physics formula number 1. V equals V naught plus AT, and D equals D naught plus V naught T plus 1/2 AT squared. So I put those things down. Then I need to answer some questions. So a car traveling at 15 meters per second passes a bus at a stop. If the car passes the bus, moves after the car with an acceleration of 15 meters per second squared. First thing we want to find is t-catch. So we say D equals D. Then we put in, what does D equal? D naught plus V naught T plus 1/2 AT squared, and that equals D naught plus V naught T plus 1/2 AT squared. So we set that equal to themselves. Remember, one has constant velocity, meaning it has no acceleration, started at 0, they start at the same time. which is different than if you choose to do t-catch on the math portion of this exam. Keep that in mind. And then over here we start at rest, so we get rid of these things, and we have 1/2 at squared. Just so happens they both have 15 for the constant velocity and acceleration, so we get 15t. Then we take half of 15, which is 7.5 t squared. And basically we want to solve for t, or factor t. We get two answers because we've got the squared term. One will be 0. The question is, what's the other one? So easy thing to do would be graph this beast. So we'll say y equals, already had something in there from something else, don't really remember what it is, doesn't really matter. So we have 15x. We come down here and we put in 7.5x squared. Now ready to graph. Here comes, whoa, my window's not cooperating. So let's fix these things. Let's make our, what would be a good thing to use? Let's make our x max. I think that's actually fine. Let's just make the y max like 150 and see what it looks like now. Constant velocity, boom. Right there's the intersection. We could even make our x max a little bit less. We can even say like, how about 5? We graph that. Ooh, I forgot to change my y max, or x negative, whatever. You can see the intersection a little bit better. So we'll do the intersect, go calc, intersect. I'm going to move over here. I'm looking at my cursor right about, okay, find that time. X equals 2 seconds, a distance of 30. So they meet at 30 at a time of 2 seconds. And there we go. So 0, 2. Now we got to do some more work here. So we need to find the velocity after 1 second. That's easy enough to do. V equals v naught plus at. Remember, it starts at rest, and the acceleration of the bus is 15, and we put in 1. So therefore, it'd be 15. Then the distance. So we say d equals d naught plus v naught t plus 1/2 at squared. Whoops, sorry about that. And we put in 0, starts at rest again. So we have 1/2 of 15 times 1 squared. So we get 7.5 for the distance. And the time at 25 meters. So how does that work? Well, we put in for d 25 of 1/2 15, or a, 7.5 times t squared. So we get 25 over 7.5 square root equals t. And that comes down to 1.8 seconds. Or you could just put in, to check that, you could put in a value of 1.8 and see, you can do all kinds of stuff. But once again, we're over my 10-minute goal here, so I think I'm just gonna stop with that. So that was the Unit 2 study guide. We got Unit 3 coming up here in a bit. All right, bud.